All right, it is an honor to be here today. I'm really excited to talk to you about our work in integrated OCT. But before I tell you what this work actually is, I just want to motivate you with why we're doing this. And it really goes to kind of a fundamental thing in medicine, which is you can't effectively treat a disease that you can't see. And this has really been true for all of modern medicine, which really, I would say, started with the invention of optical microscopy, which for the first time allowed scientists to see these tiny little microbes like bacteria and develop what is now known as the germ theory of disease, which really underlies all of modern medicine. Now, over the last 100, 150 years, our ability to image the body has grown to an extraordinary degree. Things like CT scans and MRIs allow us to see inside the body non-invasively and have completely changed the way we understand the body and diagnose disease. These two techniques alone account for over 120 million scans in the US alone. It's a huge amount of diagnostic capabilities that have completely changed medicine. Unfortunately, there's two big drawbacks to both of these techniques. One is they're massive. Like you can see these take up a whole room. They're typically in a dedicated medical center, imaging center. You need a referral, and it takes like 30 minutes to an hour to get an image. And so these are barriers to care, right? So if you need access to medical care, these are things you have to get through. Second of all, it's expensive. The average scan costs about $1,000. This is a non-trivial price, and it's a huge barrier for access for most medical diseases, unfortunately. So one of these, which I want to talk about today, is actually our ear care, ear health or hearing care. So for the parents in the audience, this might be a very familiar picture. If your child is irritable, they say their ear hurts, maybe they can't hear well, you take them to the doctor, and this is what they do. They stick an otoscope in their ear, and they take a look. An otoscope, though, it's a flashlight with a lens. All they can see is the eardrum. But the disease isn't on the eardrum, it's behind it. So how can you actually diagnose something? How can you actually treat something effectively if you can't even see it? Unfortunately, the answer is you can't. So for otitis media, which is ear infection, the diagnostic efficacy is about 50%, which means half the time you're prescribing antibiotics to someone who doesn't need it, or half the time you get it wrong and you think they don't have an ear infection when they really do, right? So this is fundamentally hurting treatment and care. And this is just one disease. If we look at something like hearing loss, which affects 1 billion people worldwide, this does nothing, right? Looking at the eardrum doesn't help you. And so most people go untreated who have hearing loss. It not only decreases the standard of living, but it also is correlated with other medical diseases such as dementia if hearing loss is left untreated. All right, so what do? How can we actually fix this? Right? We can't make CT scanners cheaper. If you know how, please let me know. So what can we do to actually improve care here? So what we started doing at Bell Labs a couple of years ago is looking at a technique called Optical Coherence Tomography. So this is a 3D imaging technique. You basically take a laser, you scan it on something that you're interested in, and you can build up a full 3D image of that thing. So it's like LiDAR, but you're pointing it inside the body instead of outside. And so you get these amazing images. So this is in a human eye. This is a live patient. It's completely non-invasive. And this is their retina. And for those of you who look at retinas all the time, you'll immediately see this is a macular edema. So if left untreated, this is really bad. This will lead to permanent loss of eyesight. But now that clinicians can see this early, they can treat it. Right? So this patient can actually keep their vision. Now still, this is amazing. It's a really, really fast technology, but it's still pretty big. Right? This is about a $100,000 machine. It sits on a big table. And because of that, really only ophthalmologists have it. Even your corner eye doctor can't afford this machine. So most people don't even have access to this. So what we did is we looked inside and we said, what is an OCT system? And really, it's just an optical transceiver. You have a laser, you send out a signal, some comes back, you mix it with a local oscillator, you detect it, you do some signal processing, and boom, you get a really cool image, right? And we know how to do all of those things here, right? The optical transceivers are kind of our bread and butter here at Bell Labs. And not only can we do the DSP part, we can actually make all of those pieces very small for very low cost, and we can make it very scalable. All right, so we've actually been doing this for decades. This is an example of an optical scanning mirror. It was developed about 2 decades ago to do optical cross connects. So I have a bunch of fibers coming in, and I have some mirrors here, and I can actually reroute the light from any fiber to any fiber. So we can do this. We can scan light very easily for very cheap, make it very low cost and size. But we can do this for all optoelectronics devices. Right? So these are some examples over the last 30 years showing we can actually take entire optical systems and shrink them down onto a piece of silicon smaller than the size of a penny. Right? We can put the lasers, the detectors, all of the optical mixing elements all into one small chip, and we can do it in a way that's mass producible, reliable, and low cost. And so what we've done is we've taken this technology and we've applied it to OCT. And so this is one of our integrated OCT modules. So that big OCT box you saw on the table, this is it. In the chip, about a size about 1 centimeter by 1 centimeter. All of the optics, all of the electronics into one tiny little package. And what's cool about it is it's using semiconductor processing. So the more of these we make, the cheaper they get. So this is really exciting to have this technology to do OCT. And so we started thinking, well, what can we do? Where should we apply this? And so we went back to the ear example. So if we look inside a cross-section of a human ear, remember the otoscope only sees the eardrum, but that's not the exciting stuff, right? All the interesting stuff is inside. Right? We want to see the middle ear bones, we want to see the cochlea, we want to see all of the space in between, and now we can. So with our OCT device, we've tested this in mice. This is a live mouse ear. You can see the tympanic membrane, you can see all of the structures of the middle ear, and this whole scan took about 2 seconds to make. And so with this technology, not only can you see all the structures, you can see the eardrum, you can see behind it. If there's fluid, you can actually tell if it's bacterial infected, if it's a viral infection, if there's strange growths, you can see it. In seconds, the clinician can now actually see what's wrong. And what's really cool is on top of this, we can actually play audio tones while we're imaging, right? And we can actually see how every single part of that middle ear vibrates in response to the sound. And so if we look at any part of this ear, what a clinician can now do in just literally a matter of seconds can get an objective audiological exam of that patient. They can see how they respond to sound, what frequencies they're not hearing, and they can also isolate exactly where in the ear the problem is happening. Is it conductive? Is it in the cochlea? Again, replacing what typically is putting someone in a sound booth and saying, can you hear this? Can you hear this? Again, we can do this now in seconds. So we really think this is going to completely transform how we address our hearing and our ear health. And so what we've done is we've taken this little chip, and we're now in the process of integrating it into that otoscope. Right? We can take this because of its small form factor. We don't need a new device. We don't need a new thing. We're just going to, what we want to do is we want to take every single otoscope in the world, and we want to integrate an OCT into it. So when you go to your clinician, they do the same thing they always do. They just look in your ear. But now instead of seeing just the eardrum, they're seeing everything behind it, and they're able to tell what's going on. And so we're spinning out a company called Astronu, and this will be our first product to actually address hearing health. So this has been really exciting because I've been working on this a long time. It's cool to actually finally see this start to go out in the real world. But from a research point of view, there's so many other things we can do with this. One of the other things I want to talk about quickly is in wound care. So this is another one of these areas that is poorly addressed in the market right now. And I'm not talking about like cuts and scrapes, but I'm talking about the millions of people who have wounds that don't heal, the millions of people who get surgery and are then at high risk for bacterial infections or other complications. And really the standard of care right now is a doctor will look at the wound and they'll say, that looks okay, or I don't know about that. Maybe we should treat it with antibiotics. And so what we're able to do is we're able to take OCT, and this is a scan of a live mouse. They have an incisional wound, and we're actually able to take 3D scans of that entire wound area. We can then feed that into an AI model, which then segments out all of the important structures within the wound, and we can now non-invasively watch as this wound heals over days and weeks. And so what's cool here is we can actually do two things. One is we can actually detect when things are starting to go wrong days or more before a typical clinician would be able to see it with their eye. Second of all, we can now actually see the mechanisms by which the wound is healing to make better treatments. So this is just another exciting area we're looking at with OCT. Now, before I end here, I just want to acknowledge all of the people who've contributed to this project. Honestly, this is the best part about working at Bell Labs. There are literally experts on everything here. And so I've over 40 names up here. I wasn't able to get all the pictures, but they were all absolutely critical to the success of this project. So I just want to thank them all. Thanks.